So, hello, welcome to one of the last talks of this year's DevVox. I hope you had a good time so far. My name is Fabian. I work for a company called Console in Munich in Germany. And I'm going to talk about unRESTful web services with HTTP2. So what is HTTP2? It's the new version of our HTTP protocol. And it was created to make the World Wide Web faster. So the goal is you have a web browser, open a web page, and the web page should appear as fast as possible. And in order to do that, the HTTP protocol was optimized and a bunch of new features was introduced. I myself, I'm not a web developer and I'm not a web page optimizer. I'm a Java backend developer. But as it is 2015, I guess everybody knows that HTTP is no longer just used for viewing web pages. So when I have two server applications and need to integrate them and need some kind of interface for them to exchange data, then the most popular choice today is basically to use REST, which is an HTTP-based protocol. So when I hear that there is some new version of HTTP that somehow helps the web developers to do fancy things, then I get curious and I ask myself, yeah, maybe some of the features are also good for back-end REST services. And it turns out that actually some of the features are really cool for REST services. It's even possible to create services with some kind of functionality that's not possible to do with traditional HTTP1. That's why I chose this title, unRESTful web services. So unRESTful saying it's kind of a REST service, but it does things that would not be possible if you tried the same thing with HTTP1. So what am I going to talk about in the next hour? First of all, I think there might be some people in the audience who did not have a look into HTTP2 yet. So I start with a quick, like my first HTTP2 request introduction. So we run a simple GET request, look at the traffic, and so that everybody has an idea what HTTP2 is about. And after that, we go through the main features. The main features are multiplexing, server push, stream prioritization, and flow control. And I will explain why they were introduced. And then we will have a look if we create REST services, if we do server-to-server integration, how can we benefit from these features? And as a wrap-up, if you go home and think, wow, cool features, I want to use them tomorrow in my project, then it's not only enough that there is some protocol that supports that, you need some environment, some tools to make sure that things really work, some automated integration testing, and I have a few links to tools that you might probably use if you start doing this in a production environment. So, but let's start with the introduction for people who did not look into HTTP2 yet. The first thing I want to say is that HTTP2 is nothing that will be available in 5 years or anything. HTTP2 is something that's available now. All current versions of major web browsers support HTTP2. So Chrome, Firefox, even Internet Explorer, if you use this version Edge, that's included in Windows 10. For Java developers, there are a lot of servlet containers that support HTTP2 already. There is Jetty, of course, one of the first. Then Netty, you might know it if you are into this reactive programming thing. Undertow, maybe you don't know Undertow by its name, but Undertow is the servlet container that's included in the Wildfly application server. So if you use Wildfly starting with version 9, it supports HTTP2. And also, if you have some non-Java infrastructure around, like an Apache server, there's a mod H2 that you can enable, and also Nginx announced that they support HTTP2 now. And even some major web pages enable it already. So if you use one of the latest browsers and visited twitter.com in the last month, then you have used HTTP2, so maybe without even noticing. If you just look at the timeline of HTTP versions, this sounds a bit strange because like in the 90s, the World Wide Web was invented and there were a few versions of HTTP. Then 16 years, nothing. And then in May 2015, HTTP2 was standardized. And now, a few months later, it's supported, major web pages use it. Seems to be not the whole story. And the missing thing here is this one. In 2009, Google started with an experiment called Speedy. And it was like an experimental implementation of a new HTTP protocol with the goal to make the World Wide Web faster. And HTTP2 is basically nothing but a standardized version of the results that came out of Google's Speedy experiment. And so all the browsers and servlet containers and everything that supported Google with the Speedy experiment, they could just reuse a lot of their code to now support the standard. And that's the reason why it went so fast that it is now available and ready to use. Before we look into a first request, I want to set a bit the frame, the expectations, what HTTP2 wants to do, and more importantly, what it doesn't. So what it wants to do, I said it already, it wants to make the World Wide Web faster. And it does a lot of things to do that, less protocol overhead, less data to be transferred, and it has few features that we'll look into in more detail in a few minutes, multiplexing, server push, whatever. That's the main topic of the talk. We will see it soon. But more importantly, I want to say what HTTP2 does not. And the very most important goal is HTTP2 does not want to break your existing web applications. So one of the main goals is that you can take any existing web application as it is deployed on an HTTP2-enabled server, and it should just work. If this wasn't the case, HTTP2 would have no chance to be accepted, or because you cannot go ahead and tell the world that all the web applications need to be refactored now. So what does that mean, compatibility with HTTP1? It doesn't mean that a HTTP1 client can talk to an HTTP2 server. It means that the things that the HTTP1 protocol exposes to the application, as the interface that an application uses, this interface stays the same. So what is this? The first thing that an application uses is it sees that HTTP is a request-response-based protocol. So everybody who ever implemented a servlet knows that. There are requests coming in, responses going out, right? These requests are these get, put, post, delete, whatever. And this stayed the same. So if you have a servlet and you implement a do get, do post, do delete, whatever method, it just works the same with HTTP2 because HTTP2 has the same request-response-based mechanism. The next thing an application sees is that these request-response things are stateless. And this is something we all have kind of trouble with because we want to have some state. A user should be able to log into a web page. Then when the user comes back with the next request, the user should still be logged in, so we need some kind of state. And I think everybody in the audience knows how we deal with it. We introduce cookie headers and associate cookies with HTTP sessions on the server side. And that's what existing applications do, and so this thing didn't change. It's the same as before. Everything underneath, the way the data is exchanged, that all changed. It was refactored really a lot, and there are also some new features that applications might use but don't need to. But everything that you have in this current servlet API or everything that some web application does sees just the same interface. So that's the scope of HTTP2, so to say. But let's start with an example. I will quickly show a demo, but first there's one more thing I need to tell you in advance. It is that HTTP2 only works with SSL connections. This is kind of not 100% true because the standard also allows some clear text connections, but they are supposed to be more for debugging, and some of the major browsers only don't support it because they want you to use HTTPS with HTTP2. And also, if you use clear text HTTP2, you will have trouble with proxies and firewalls and whatever. So whenever you use HTTP2, you use it via SSL. And normally, for a Java developer, it shouldn't really matter because you say to your API, give me an SSL connection, and you get one. But there's one reason why this SSL connection establishment kind of affects Java developers today. And so I need to give a very quick introduction what the problem is. If you really want to know what happens and what kind of packets are sent back and forth and how the latencies are, there's a really good book that I can recommend. I put it in this star on the top right corner. It's by Ilya Grigorik. He, maybe you know him. He's a web performance evangelist at Google, and he wrote a book called High Performance Browser Networking. It's an O'Reilly book, but it's there for free under this URL. So that's the initial letters of high-performance-browser-networking.co. If you go there, you find a lot of resources, a lot of these images, and you really understand what's going on the wire. But what's important for us now, if you use SSL today with traditionally HTTP1, what you do is you create a TCP connection. Then on top of that, you create an encrypted channel with this SSL handshake. Once you have that encrypted channel and you want to use it for some protocol, like for example, WebSockets, then you send an HTTP upgrade header and switch to WebSockets, and then you can start using the connection for your actual application data. And as you see, it takes a lot of round trips before the first application data actually can be exchanged. And so with the introduction of HTTP2, this was optimized a bit. And the idea is to slightly modify the SSL handshake. There's this new thing called ALPN. It's the Application Layer Protocol Negotiation. And it means that there's a small additional field that's exchanged there. And within this additional field, you agree on what protocol you're going to use once the encrypted channel is established. Which means once the encrypted connection is there, you agreed already that you want to use it for HTTP2, and you can start speaking HTTP2 right away. Without that, you would need an additional HTTP upgrade and tell the server you want to switch to HTTP2, and you would have an additional round trip. So that's a bit more efficient, but what does it mean for Java developers? It means that the underlying SSL implementation needs to support this additional field, this additional ALPN mechanism. And this is something that's a bit tricky because SSL is implemented in the Java runtime. It's some package Sun Security SSL. There are open source jar files that provide implementations of this that support ALPN. So you basically just download it and use the version from the jar file instead. But the tricky thing is that, that you cannot just put a jar file in a class path and then replace some classes that are defined in the Java runtime. You know, the Java runtime does not allow for replacing its own classes with something from the class path. If you want to do that, you need to start the JVM with an additional parameter. Do you see my mouse? Yeah. It's this one here, boot class path. And if you start your JVM with this additional boot class path parameter and specify this jar file that implements SSL with ALPN, then you're fine. Then your SSL implementation can do it and everything works. And you will never have any problems with it. It just works. It never crashed for me and no problems at all. It's just that you need to remember to use this. And if you forget it or don't use it, you will not be able to create an HTTP2 connection. This is only relevant for Java versions that came out before HTTP2, which is Java 7 and Java 8. The next Java version, Java 9, comes out after HTTP2, and it will support ALPN. So once Java 9 is there, this workaround will no longer be necessary. There's this JEP 244 that aims at implementing this new thing in the core SSL implementation. Good. So it was a quick introduction. Let's go to a demo and view a first HTTP2 request. I have a really, this is the source code of the most trivial thing you can do, a servlet that takes a GET request and responds with hello world. I have implemented it with, where is it? With embedded Jetty. So there's a Jetty version that you can start embedded, with a regular main method. And I put this main method in an executable jar file. So I can just start it with java-jar. The only thing I need to do, as I have said, this additional boot class path parameter here with the SSL implementation. So I started see if it works. If I go to HTTPS localhost, I put it on port 8443. Probably very small, but it says, where is it? Let's refresh. Hello. I don't see that. It should say hello world here. I think I saw it for a second. I don't know. But it basically works. But I want to show you. Okay, let's try. Just close this window. Try new tab. Localhost. There it is. Proof it works. Yay. So, but what we want to do, we want to see the traffic. You know, we want to see what's going over the wire. And what you do for that, usually you use some command line tools. So if you just use the Chrome's developer tools, it displays the traffic the same way as it displays HTTP1 traffic. So you cannot really inspect HTTP2 protocol specific stuff there. So you need some command line tool. And, oh no, that was the wrong direction, like this. And now comes the first message that might, I don't know, maybe not so nice for everybody, because HTTP1 was an ASCII-based protocol. So the Unix hackers could use standard tools like Telnet or maybe Netcat, or if it's an encrypted connection like OpenSSL. And then once you get the traffic, you can just dump the stuff that's going over the wire to your terminal, and you see what's going on, because HTTP1 is human-readable ASCII format. With HTTP2, this was changed. HTTP2 is a binary protocol. That has mainly two reasons. The first, and I think most important reason, is that this enables HTTP2 encoding to be more efficient, so there's less data to be transferred, and that reduces the latency when you view web pages. And there's another reason. When you implement a parser for HTTP2 in code, then it's much easier to do than to implement a parser for HTTP1, because the format is quite simple and quite clear. On the downside, if you want to see HTTP2 traffic, you need some specialized tools that do that. So you cannot just use Telnet anymore. There is a tool that everybody knows, curl. There's a curl version that supports HTTP2, actually. But curl has a bit of a problem why I didn't use it, because what curl does, it runs some requests that you specify, and then it terminates it again. And what I wanted to have is a little tool that just starts a background process and leaves a connection open for a longer time, because later I wanted to play with push messages, and in order to receive push messages, then it must be some open connection that the server can use to push data. And because this wasn't there, I just did my own little thing. So I have the GitHub URL on the bottom of my slides, but it's only for use in HTTP2 demos, so it's no other use case. So you start the background process with start. So this is where all the traffic goes through. And then in another terminal, you can run requests. The nice thing is, as here all the traffic goes through this process, it was easy to implement a dump parameter that additionally just dumps all the traffic to the console. So if I type connect to the server, port 8443. Oh, what? Localhost. And then get some path. Here, hello world, it works again, very reliably. So let's look at the traffic. Can I make this larger? So we don't want to go through all the traffic here. The main point I want to talk about is that you see that the HTTP2 traffic is split into small chunks, and these chunks are called frames. And the frames have a maximum size. So in HTTP1, you can have potentially infinitely long messages, so to say, and they will be all transferred until they are done. In HTTP2, that's not the case. HTTP2 is chunked. It has single frames. The frames have a maximum size, and one frame after another is transferred over the wire. That's important later for the multiplexing, because as the whole traffic is just a sequence of chunks, you can have many requests in parallel, response messages coming in, and so If you want to split HTTP messages into chunks, there's one thing that comes really natural and that you want to do. An HTTP1 message is composed of a header part and a body part, or in many cases, only a header part in the GET request, for example. And that's a natural place. So in HTTP2, we have a headers frame, like this is an outgoing headers frame for the GET request. You see it's a GET, and this is the path, so you find everything again there. And now for the response, this is the headers frame again, like with status code 200 OK. And this is the data frame. So what used to be the message body is now called data frames. And this data frame has 13 bytes payload, so that's the length of the string hello world. If the content would be longer, like if it was a JPEG image with 5 megabytes or something, then there wouldn't be only one data frame, but a sequence of many data frames, right? And here's a little flag, end stream, that tells you if it's the last one or if there are more to follow. Good. Let's go back. So, whoa. Hello? Ah, yeah. So, it was a quick intro to show you how HTTP traffic looks. And I guess so now you have a rough idea what it does, and now it's time to jump into the cool new things, so to say. And the cool new things are multiplexing, server push, stream prioritization, and flow control. Let's start with multiplexing. That's I prepared already a bit because I told you that the traffic is chunked into frames, and frames have a maximum size, and so it's possible to do many requests in parallel. One more thing in this demo. Can I switch there? What? Maybe importantly. So when there are more than one request going on at the same time, then somehow the client and the server need to know which frame belongs to which request. And this is done via this little number here. This is called the stream ID. As there's only one request in the demo, there's just stream ID 1, stream ID 1, stream ID 1. All these belong to one request response pair. Like a pair request response pair is called stream in HTTP2. If there were more than one request going on, the other requests would have different numbers. So that's how frames are related to the request response pairs. So multiplexing now uses this to be able to do many request responses in parallel, and the effect of this is very well visualized with a small demo. I created a Docker container with that demo, so I can just run it locally. This demo actually comes from the guys who did the HTTP2 implementation in the Go programming language. And what it does, larger, scale it in a bit. Yeah, what you see here looks like a big picture, but it's actually composed of a lot of small pictures. And the server delays the delivery of each small picture by 200 milliseconds. And now I'm loading it with HTTP1. And what happens is, it takes some time until the whole web page is there. So why is that? Because the web browser sends a request, server delays the response by 200 milliseconds, then the response comes in. And while the request is running, the connection is blocked. There can be nothing else done with the connection at the same time. The browser has to wait until the image is there. Only then it can use the connection to issue the next request. Then it gets the next response, and so on. And this is a very inefficient use of the connection capacity because the connection is idle most of the time. But with HTTP1, there's nothing. There is nothing the browser can do. The browser can optimize it a bit because the browser creates not only one connection, but maybe 5 or so. I don't know how many. But if you have few resources, like a few more than 5, then you see that it results in a real delay. So if you load the same thing with HTTP2, you see it just basically comes immediately. What happens? There's only one connection, so that's one basic principle with HTTP2, you have only one connection, leave it open, use it for everything. And over this one connection, all requests are sent at the same time. Each request is delayed by 200 milliseconds still, so the server side didn't change. But then after 200 milliseconds, all the resources are sent back at the same time, like using multiplexing. And you see the effect, it's a lot faster, obviously. So what does that mean for REST services? Do I have any? In REST services, we basically have the same problem. If we have a REST server and there's one request that takes some time to be processed, then the client connection is basically blocked until the server responds. What can we do about it? We can basically do nothing about it. So we can either ignore it, and then the client is just slower, because when there's a long-running request going on, the connection is blocked. Or we can be as clever as a web browser and open not only one connection, but more than one connections in parallel. But yeah, what does that mean? I mean, that means either we limit the number of connections somehow and create a connection pool, and then we need to size the connection pool, and if the load gets high, then all the connections in the pool are used, and it's kind of difficult to do, and it kind of only delays the problem, because if the load becomes more, then the connection pool is used. Or we don't take the effort to maintain connection pools and just fire new connection with each request. And then we have kind of a danger in our system, because it might run well for a long time, but if the load is such that the frequency with which new connections are created is higher than the frequency with which old connections are cleaned up, then like the number of existing connections will pile up, and then at the end of the day they will basically run into some limits. I don't know, no threads left or no TCP ports or whatever, and basically this will kind of halt your application, or something weird will happen. And like whatever you do, it's either very complex or like you need to find some trade-off, and it's hard to do. With HTTP2, things are easy. You just create one connection, use multiplexing, and if you have a long-running request, just long-running, but still you can use the same connection for short requests in the meantime. So there's just you don't need to put much effort into doing these things. I have a few examples how this would look like with current Java implementations of HTTP2 clients. Also, just to show you what Java clients are out there. The problem is here, I mean, it's not really a problem, but it's kind of what you need to do. If you want to use multiplexing, you need to implement an asynchronous client. So if your Java code is synchronous and waits after each request until the response is there, then it doesn't help you that the underlying protocol would be asynchronous, So, and there are a few HTTP2 clients out there that support this. One is OkHttp. I think everybody who has to do with Android development knows it, and it also works pretty well on the server. And it's like the typical asynchronous way you do things. You create a request, but instead of sending the request right away, you enqueue it somewhere, provide a callback, and the callback has an onResponse method, and then this will be called once the response is there. So in that way, you can just use a connection for multiple requests in parallel. Another client is Netty. I mean, Netty is basically more known for its non-blocking server, but Netty also comes with an HTTP2 client library. There's an example code in the Netty GitHub repository. It's pretty verbose. It's like 4 classes and showing all kinds of things you can do. But at the end, it all comes down to the same thing. So you have kind of a response handler with a message received message, and this is called once the answer is there. So it's the same idea, but a little more code. And then there is Jetty. Jetty has two. Actually, I mean, Jetty is basically an HTTP2 a servlet container, but Jetty also provides an HTTP2 client library, and the client library provides 2 APIs. So one is high level, and it looks pretty much similar to what we saw with OkHttp. Then there is a low-level thing that like allows you to really, like when you do a request, that you create your headers frame that you want to send and create a new stream explicitly, and then have like methods, the callbacks that are called when frames come in, and you can just like view the results of the individual frames you receive. So if you want to play really low level with HTTP2 features, that's the way you could go. And when it comes to standard clients you could use, I mean, there's actually in Java SE, in the regular Java, there's just one HTTP client that is called the HTTP URL connection. And I don't know how old it is, but very, very old. Don't know, Java 1.1 or so. And actually, as now this whole HTTP2 thing is going on, there is an attempt in JEP 110 to implement a more modern alternative to that, and that will probably go into Java 9. And then in Java 9, you will also have a basic HTTP2 client where you can do basic things without using an external library. What's with Java E, I actually don't really know, to be honest. Good. So this was the first new feature I wanted to show you, the first thing that you cannot do that way with HTTP1. I think it's pretty cool. So for me, it's actually my favorite feature because it makes the clients much simpler, much more robust and everything, much more responsive. But maybe you're not yet so thrilled because it basically just solves like non-functional requirements. There's no real new things you can do. It's just that the things you do work better somehow. But now we come to server push, which is really a cool new thing. And server push, I need to explain a bit what it does. Because when you just read the name, you maybe have some wrong associations, like that it's kind of a new WebSockets or so. But server push is actually, it's very easy to explain it because it does exactly one thing. It's exactly for one specific use case to solve this. And the use case is the most common thing that happens in the World Wide Web. A browser accesses an HTML page on the server, and the server delivers the HTML page to the browser. Now, within the HTML page, there are probably links to CSS files, JavaScript files, images, and so on. So the server basically knows that very likely this client will come back in a few seconds and request the CSS files, images, JavaScript, and so on. But the server cannot do anything. The server just sits and waits and waits and waits. And once the other requests come, the server says, yeah, I knew that you probably need these also, right? And that's some point where HTTP can be optimized. And that HTTP2 optimizes quite a bit. Because what happens with HTTP2 is when the server knows that the client will probably come back and ask for a CSS file or JavaScript file or image file, then the server does not need to wait for the actual request coming in. The server can just create the response and send it right away to the client. So what happens then? The client receives a response for something that he has never requested, and he takes the response and just puts it in some cache, right? And once the web browser is done processing the HTML DOM structure and comes to the link where the actual CSS file is linked, for example, then the web browser issues a GET request, but the HTTP2 stack within the client says, oh, this request, I have the response already there, it's in my cache. And then the request is responded right away without any additional network traffic. And I think this is a pretty cool solution because it means from the application point of view, like the web browser being an application now, nothing changed. So the web browser makes a GET request, gets the HTML page, makes a GET request, gets the CSS file, and so on. So it's all compatible, works the same way as before. But when you look at the actual network traffic, there's a whole lot of optimization going on. So the traffic is very differently than you might think it is. The second GET request doesn't even trigger network traffic, and there's this push message being sent to the client and so on. So I think it's a really cool way to optimize these things while still being compatible with the HTTP1 semantics. When we think of, maybe first thing, it's actually easy in Java to create these push messages. So you build a request in your memory somewhere because it doesn't come from the client, and then you call push, and then this request just goes through your servlet stack and comes in as any other request, and like the response is sent out. And it will be part of Servlet 4.0. So this is now proprietary Jetty code, but with Servlet 4.0, you don't even need any external dependencies for that. So let's think for a moment of what we can do with this with REST interfaces. And REST interfaces, basically, I like them very much because they're very clean and very simple and very nice. And when you have nice resources and verbs and so on, it's really easy to understand what's going on when you see a REST interface definition. But there's always one thing that doesn't work well with REST. And this is when the client needs to be informed when a resource on the server side changes. So, I don't know, the server counts something or don't know, and when the count goes up, it wants to kind of inform the client. So what can you do in that case with your REST interface? Basically, you need to do polling. So the client every second just triggers a GET request, gets the status of the resource. Next second, triggers a GET request again, gets the response, and so on. So that's the only way you can do it when you want to stick with the REST interface. And it's also the preferred way. I mean, if you kind of can live with polling and can do it, and it has not too many drawbacks, then it's the way to go because it's very robust, it works everywhere, and you still have a REST interface. However, as you all know, with polling, you need to do some trade-off. The more frequently you poll, the more unnecessary network load or also load on the server you create. And if you reduce the polling frequency, then the time when something really happens on the server, the delay until the client gets this information increases. So you have to find some trade-off you can live with. And in order to avoid these trade-off, the people do all kind of crazy things like that. We create REST interfaces and they say, okay, but for this specific use case, we don't really use REST, we use WebSockets instead, or long polling, or whatever kind of not really REST, not really HTTP stuff is going on there. So what can you do with this server push now? The first thing you can do, of course, when your server sees that a resource changes and the client would be interested in that, the server can create a push message. That helps a little bit because the client polls very frequently, but when the client polls the next time, the actual response is already there. So the polling request goes a little bit faster when actually something happens on the server. So that's a bit of an optimization, but not very thrilling. But when you have a client and you learn that whenever something really happens with the resource, you get a push message from the server, then you might modify the loop that polls a little bit. Because usually polling is triggered by a time interval, like every second or so, but you might modify this trigger. You might say, okay, maybe my polling loop goes once a minute, just to be sure, but in addition to that, my polling loop is triggered whenever I receive a push message. So what do you end up with then? You kind of still have a REST interface, you still have this regular polling semantics, you still have a client that uses GET requests to query the state or the value of a resource, but you don't need to do this trade-off anymore. You know, using when your polling loop is triggered whenever a push message is received, then the delay when something actually happens on the server until the client receives it is really low. So you have no disadvantage there. And on the other hand, you don't need to switch to any WebSocket or long polling or non-standard protocol. You just use the real REST semantics. You really use HTTP2 as it is supposed to be. And even if it fails, if for some reason there's some network component that causes that you cannot use HTTP2, the only thing that changes is then you just revert back and trigger your polling loop every second again. So you're kind of, without having any major disadvantage. You can like use polling, but get rid of this weird trade-off that's associated with it in HTTP1. And that's something I like really very much. There's one drawback a little bit. In order to do this, you need to have a client library that allows you to provide a callback that is triggered whenever a push message is received. This is easy if your client is a Java client in some kind of backend system, because all the libraries, OkHttp, Netty, Jetty that I showed you, they're open source libraries and you can put callbacks wherever you want, basically. Yeah? No problem. If your client is some JavaScript in a web browser, then you cannot do these kind of things, because the web browser doesn't expose like any low-level HTTP2 features to the JavaScript API. So in JavaScript in a web browser, you have no chance to like provide a callback that is triggered when a push message is received. So basically, server-to-server integrators, backend developers can do more fancy stuff with HTTP2 than the actual front-end people can do, which is nice. Good. That was server push. I mean, the most amazing feature probably. There are two left, but they are really like easy to explain. It's stream prioritization and flow control. Stream prioritization means that, like, originally in the web world, you want that messages that deliver content are processed earlier than messages that deliver just some fancy graphics stuff or something. So that the goal is that the user can start reading the web page right away, and some JavaScript that's only painting the button green or something can like be delivered later. And in order to support that, there was some stream prioritization introduced. It has like two mechanisms. One is some priority field, which is kind of an integer that tells you how important this response is, like from between 0 and 255. And the other feature is some dependency trees. So you can mark a response and say, okay, when this response depends on another response, and then the other response should be processed earlier. But all this stream prioritization stuff is just, it's just additional fields in the protocol. So it depends on the client if the client actually does something with this information or if it doesn't. So if you just, as a server, put some priority fields somewhere and the client doesn't respect them, you don't gain anything. But if you have a use case where you have kind of, some normal messages and some really business critical messages, and you implement a client for that and you want to have some kind of prioritization, then you don't need to invent any additional application layer stuff. You can just use these fields that are available on the underlying protocol. And then there's flow control. Flow control is also pretty simple, but for some use cases pretty powerful, because what does it do? As I said, HTTP2 supports multiplexing, so there's a lot of parallel requests potentially going on within one single connection. And what you want to avoid is that if you have one very large resource, like you have a REST service, and this is called once a day, and it gets your 2 gigabytes SQL dump, right? Then you don't want that the connection that the whole bandwidth is used by getting this dump, and other important messages don't get through anymore. And so what HTTP2 allows you is to limit the available bandwidth for a specific request or response. So you can basically say if you have that strange service that gives you the 2 gigabyte dumps once a day, you limit its available bandwidth to a certain number of bytes per second, and that way you make sure that there's still bandwidth available for other stuff that you would do in the meantime. I mean, in most cases, I think you will not need it, but once you have like large messages or want to limit something, it's really useful that the underlying protocol supports it. And that's also something that's implemented in the transport itself. So once you specify this, there are some like callbacks, some flow control strategy interfaces that you can implement. This example comes from Jetty. And once you implement this, it's sure that the underlying protocol really respects that and uses the bandwidth in that way. Okay, So that was it basically for the main headline features, so to say: multiplexing, server push, stream prioritization, and flow control. So if you are excited about these new things and think, okay, I want to start using it, it sounds really cool, then basically you need some way to test it. Regular unit tests won't help. So if you have your service that uses server push messages to trigger some action on the client, you can have a unit test to just figure out if the right business logic is triggered or something, but you need a real test with a real network interface to make sure that this push message is handled correctly in the client stack, right? And one way to do it with a real network connection is this Arquillian Cube. There was actually a talk about Arquillian Cube at this Devoxx. And what it does, basically, it starts a Docker container, so you can define a predefined Docker container, and within the Docker container, you could just put a wildfly, for example, with HTTP2 support enabled, and then Arquillian Cube will start that container when your tests start, and then you can use Arquillian to deploy your web applications there and run your tests against that. And so that way you have real network communication from your host to the container. There's another alternative. It's a bit more lightweight than Arquillian Cube. It's this Docker Maven plugin. You can use it to start Docker containers at the beginning of your integration tests and stop Docker containers at the end of your integration tests. But during the tests themselves, you don't have this Arquillian that you, for each test, deploy new WAR files or something. It's just, if you want to create one container and use it for your entire test run, then this is a bit more lightweight than what you can do with Arquillian Cube. Docker is pretty cool for testing it because you can just, you can create a Docker image where everything is configured and HTTP2 works and so on, and you don't need to care about it. And once you have Docker, you can just run your tests and they will work the same everywhere. But Docker cannot be used everywhere. I mean, first of all, you need to have admin rights on your machine, which is maybe not the case sometimes. Second thing is, you need to have some way to share your Docker images. If you're working on an open source project, it's simple. You should just push them to Docker Hub and download them from there. It's infrastructure for free, so to say. But if you work on a closed source project, you basically need some kind of internal Docker repository in your company, and you might not have it. If you don't have Docker, there's the OkHttp project that implemented this client that I showed you. They also have a very nice MockWebServer. So it's really simple. You kind of script it. You say, okay, here first response should return this response body, second response this one, third response this one, and so on. And then you start it, and you can then query it with real HTTP2 requests. It works really well and doesn't require Docker, but as I told you in the beginning of the talk, if you want to use HTTP2, you need an SSL library that supports HTTP2. So that means when you want to start that for testing HTTP2, you need to start it with this special boot class path parameter that you need to have HTTP2 support. How do you do that? Usually you start integration tests with the Maven Surefire plugin, and you can just put a JVM parameter into your Maven configuration. However, the version of this jar file depends on your JVM version. So if you have Java 8 build 40, you might have another jar file here than if you have Java 7 build 30 or something. So that means that when you do this, you need to be aware that it probably works for you, but if somebody else checks out the same project and starts to run it, and this other guy has some other Java version, he needs to basically go ahead and edit it and download a corresponding ALPN jar file there. So that's a bit of a drawback. That's better with Docker, because in a Docker container you can just have your Java there, have your ALPN jar, have everything predefined. But on the other hand, once you have done this, it's just plain Java and you don't need any other infrastructure. Okay, so basically, that's it for my introduction on HTTP2 and how you can use it for creating REST services that can do a little bit more than you can do with HTTP1 today. I have a few links. There's other guys apart from me doing HTTP2 talks. One is Adrian Cole, who committed a lot to this OkHttp project. He was at Java Zone this year, and they put their videos on Vimeo. Then there's this other HTTP2 talk in the other room. It's by Simone Bordet, and he also talks a lot about HTTP2. He's the guy who did the HTTP2 implementation in Jetty. So basically, I didn't, when I created the slide, I thought we still have this parlays thing, but as Devox talks are now immediately available on YouTube, you basically can forget it and just watch his talk if you want to learn a bit more and how Jetty does it or whatever. And then there's this very highly recommended book by Ilya Grigorik, High Performance Browser Networking, O'Reilly book, but available for free as an online version. So if you want to dive into these topics and see what HTTP2 actually does and what kind of other optimizations it has, it's really highly recommended. So thank you very much. I hope you enjoyed it a bit, and I hope you got a bit curious what HTTP2 is, and hope you will look into it. Have a good trip home, everything. Hope you don't fly with Lufthansa. They are on strike. Yeah, thank you. Is there a question, or we have a few minutes? I don't see. Yeah? What? Oh, if there is any plan for having a standard API for JavaScript for push notifications in the browser. As far as I know, there's no such plan. But I'm a back-end developer and no front-end developer, so maybe my knowledge is not so reliable there. Okay, so I would say have a good time. If you have any more questions, so just come down. I'll be here for a few minutes more.